All right. Hi, everybody. So I'm going to talk to you today about some of this work that we're doing that's going to be some exciting shock experiments. This is just the beginning of this project, but it's a collaboration led by Stephen Jarrett at Kingsborough College in New York. And we are collaborating with JSC, the American Museum of Natural History, UFC, Naval Research Laboratory, and myself at Oxford. So what we want to do is try to look at um, one of the effects of space weathering. So space weathering, if you haven't heard already, is kind of the umbrella term that we use for everything that happens to the regolith on the moon, with the main components probably being micrometeorite bombardment and solar wind irradiation. So we want to try to pull apart some of these effects. And what we're going to do then is look at the shock effects that you get from impacts and see if we can't characterize those a bit separately and see how those match up to some of this space weathered material. Can we pull apart these two major contributors and figure out what exactly those effects are? So we see a lot of these effects optically in the soils. We also see them spectroscopically. So over here, I'm showing a plot of MCube data from Peters et al. 2016. Basically, you can see that in the spectra, as you get to more weathered materials, you have a decrease in your overall reflectance, you get a stronger slope, and your features become more subtle. Uh, and there have been prior experiments where we have looked at shock by itself and seen that this does have quite a few effects. Optically here, this is an example from Jarrett et al. 2018. This is looking at bentonite. And you can see from the unshocked material to the shocked material, there's quite a bit of difference. You can visually just see how much darker it's gotten. You can see some of the deformation affecting that material. I mean, again, this is like a pretty strong pressure that we've shocked it at. But so this is one of the extreme cases, but we can see these things. So can we then use a material that's a bit more comparable to the lunar regolith to do similar experiments and characterize them both optically and spectroscopically? So our project is to use the still water anthracite a sample. And so we can see it here. This is a small core of it. It's got an A number of 92, so it's getting better towards an actual anorthite material that we'd see on the moon. And our overall idea is then to take this material and examine it both as slabs and as powders. We're going to do try to do a full characterization of this material spectroscopically and optically prior to any of these shock experiments. So that's where we've gone to so far. And so this includes both SEM and a full infrared spectral characterization. So I've been in charge of that. I'm looking at about 0.7 to 25 microns reflected spectroscopy. After we've got all of that taken care of, we'll do the shock experiments. We have about 20 shots that we can do. So 10 for the slabs, 10 for the powders, and then maybe if we need to redo anything, we have a couple extras that we can probably throw in there. And then afterwards, what we're hoping to do is we'll get back, kind of fragmented material. So we'll hope to put some of those in thin sections to examine those, look again for those characteristic shock effects, see if that deformation and do a good comparison between what we saw prior to shock, compare that then to some actual space weathered materials in thin section for both the slabs and the powders. And then hopefully we'll have enough material to then repowder some of that and see what that mix might actually look like. If we're doing remote sensing studies, we're not necessarily going to be able to see all of these details. So what might this look like after it's been re-regolithified, or basically? So yes, so afterwards we'll do another full characterization with both infrared spectroscopy, and then we'll send it over to the Naval Labs with Kate Burgess. She's going to look at it in TEM. She's had a lot of experience looking at space weathered materials, so she's going to look more in depth and see exactly what kind of similarities we can see between the two and really well characterize that. Okay, so looking at the materials. So first we're looking at the powders. So I did a, a preliminary study, basically just crushed up some of the material, pulled out some bigger bits, pulled out some smaller bits, used the mix to do just kind of a general comparison of what those reflectance spectra look like. So those are the spectra in colors. And then the final powder is about less than 30 micron grain size or particle size, and that's in black on these plots. The features don't really change, which is good. We don't really see any kind of preferential mineralogy with particle size, so it's a good heterogeneous sample. And most of the differences that you can see in these plots are due to the particle size of the material. There is a bit of difference going on in the mid-infrared, and that's also mostly due to particle size, where we get some of the features being a bit washed out because it's getting so small. So that's where it's really nice that we have the larger bits, because we can see the features aren't really changing, and then we can use that to compare later. But overall, the powder gives us a nice anorthitic composition. So the slices, oh wow, you can't see that at all. Uh, the slices are where things get interesting. So I showed you that little core that we have. So that's about a centimeter in diameter, and each slice is about 0.5 millimeter thick. And even within that, we see quite a bit of variation that we weren't necessarily expecting. This is a natural rock sample, so we should see some variability. But even between slice, when you cut each 0.5 millimeter sample, you get quite a bit of change. And what we saw just looking in one sample is that we have spectra that show very obvious quartz signatures. We do see the plagioclase, we see some kind of glassy bits that we can't identify. But basically, I was able to do 8x8 grid maps across each of these slices. So we've got 16 little discs overall that we can use for this experiment. I measured front and back of all of them so that we could get a good understanding of what exactly we're looking at, what kind of variability we see there, compare before and after. This is a backscatter electron image. Hopefully you can see it on the sides. This one is more uniform than others, but still you see a bit of variation there. And what we are then able to do is compare when we take the overall kind of compositional analysis from both the backscatter composition, which was done by Marina Gemma at Stony Brook. So she came up with this plot where she found quartz, feldspar, sulfides, and a bit of other material in each of the slices. Whereas when I was looking at the spectra, I kind of pulled out 4 categories to try to compare, and I also found quartz, 2 flag-esque spectra categories, which are just kind of distinguished by the CF shifting a little bit between the two. And then a last, which is, I couldn't really identify, but it looked like something was probably there. But overall, while the numbers might not exactly be the same, they do kind of match up quite well. The total plagioclase content from the BSE to the infrared is quite similar. And the variations that you see in these spectra here, there's quite a lot, and we think this is probably due to orientation effects, as well as the fact that when you're looking at this kind of spot size, which is about 200 by 200 microns, we're going to get mix in there. So I can definitely see some that have clear quartz and feldspar features within them. So that also contributes to a little bit of the variation between the two. But overall, this might be hard to look at as well. So these are all of the slices that we looked at. This is Marina's BSc compositional analysis versus my spectral analysis. Again, the values are not exact. but I think the trends show up quite well, so that's a good sign for this test. And then from that data, we were able to kind of pick which slice we thought would go best for certain pressures. So from previous work, we know that there are some critical pressure regimes where we expect more transitions to occur. So for feldspar, especially the transition into mescalinite. So we're able to switch out the samples accordingly and match up which slice we want to go to which pressure. And hopefully that all those labels worked out and they have it at JSC and we'll pick the right ones that we wanted. So for example, you can see here in the middle, this one has a ton of quartz in it, so we just threw that one out. But yeah, so that's kind of where we are right now. We've had a couple shots off so far with the powders down at JSC, so hopefully we're just gonna wait for the rest of the summer for all of those other shots to be fired, and we'll get some really exciting mineralogy to look at in the next couple months. And I can show you those results later at the next conference. But anyway, so that's where we're at, and I'll take any questions. Thanks.